So you all can hear me. Hello, good evening. So welcome to another session. So just for to confirm it one more time. So you people are able to hear me?
Yes.
Okay, thanks. So this is our second tutorial session or problem solving session. Uh, uh, so last time around, like we discussed, like just a second. Yeah, right. So last time around, so we discussed some problems related to last week's topics. So today, like our plan would be to go through the assignments which were discussed, uh, or I mean the assignment, the last week's assignment. That is basically assignment one's problem. So we'll go through them, like we'll discuss and also if possible we'll go through some new topics that was introduced in this week and their uh, related problems. So okay, this is uh, week two problem solving session. So yeah, right. So these were the topics we went through yeah, last time around. So we'll see some more questions related to these topics, which were basically given in your assignment, in your assignment one, and some uh, other new topics that maybe we'll see today, and the problems. So, so before that, like there was one problem last time around when I left. So I left out a problem to work out here. So actually, I asked you people to give it a try. So so in any case, like if you missed out in doing that, like maybe I can tell you what was that. So. So while discussing this linear independence topic, so uh, like I told you, like even you people already aware, like if there is a set of basis vectors and to know whether they're linearly independent or not. So like this was the like condition. So based on that, like we did a question. So, and that was like there were these three vectors, v1, v2, and v3. So, and it asks like whether they are linearly independent or not. And we found like upon checking, we found that like this is that they are not linearly independent because you would see that at the end they were forming a system of solutions because we need to find A1, A2, A3 individually going to zero. But that wasn't the case. So we found that like instead of that, like the solution of A1, A2, A3, like they were dependent on each other. Basically, A1 and A2, they were dependent. So and also with that we found they were forming a many non-trivial solutions. So, related with this, I like appended one more question to it. So, suppose if there is a vector v2 prime, such that v1, v2 prime, and v3. Now they go linearly independent or dependent. If we just simply go with a v2 prime, such like let's say some arbitrary vector we are taking xyz, this v2 prime, and now we want to see that this v2 prime will they follow this linearly independence or not. So so that was the thing like which I was like asking you people last time around. So yeah, and so let's say like if this v2 prime is independent, linearly independent with v1 and v2. So what I mean, v2 prime is linearly independent v1, v3. So uh, that means you can write a1 v1 plus a2 v2 prime plus a3 v3 equals to 0. Basically, that was the condition which I have written here. So then if that is so, then that implies a1, a2, and a3 all individually goes to 0. So so again, like from now using this new vector uh, v2 prime, you can construct the same sort of differential. I mean, same sort of system of equation, just like last time around. So uh, this time, like if you plug what is v2 prime, like you will see that xyz will appear. So you will you will get the first equation, something like a1 plus xa2 plus sorry plus a3, and second equation a1 so a2, then so I just did this same thing last time, like which I did. So uh, instead of this v2, I have v2 prime, which is xyz. So that I have plugged in and I got this equation. And now you can see that our now our aim is to know what xyz are. So that will construct a v2 prime, which we are looking for. So like from 3 you can see that this 3a1 is basically equal to minus g a2. So uh, that means now for linear independence, as I was telling here, we want a1, a2, a3, all of them has to go to 0. So uh, from here you can say that like if we have like if we impose or if we enforce a2 equal to 0, uh, not a2, uh, I mean, we want A1 if we let's say we can enforce A1 to go 0, then we will see that Z will come out to be 0. Because why I haven't set A2 to be 0, because you can know we want Z from here. We don't want I mean we are constructing a vector v2 prime which is whose elements are x, y, z. So from here, if I have to calculate g, so that g would be something minus of 3a1 over a2. If I would have set a2 to be 0, then this could have been not defined. I mean, if I could have set a2 to be 0, then like this would be whole thing would be something infinity, like which is small we are looking. So we have taken xyz to be something some finite elements. So that's why you can enforce a1 to be 0, and there upon enforcing a1 to 0, you will get z equals to 0. So uh, then uh, now let's say this z equals to 0 which you got, now you put this z equals to 0 in not z equals to 0, I mean this a1 equals to 0 which you enforced here. So you put this on other equation, that is, let's say, on second equation. So 2 times of 0 plus 0. So that will give. Now same way I can enforce A3 to be 0. Doing that, like I will get um, y to be 0. I can now use this in other equation. I mean the one which is left, the first equation. So you can use both, uh, uh, like A3 equals to 0, uh, and also the one which we imposed earlier, A1 equals to 0. So what you will get, like from there, like from 1 you can get, so A2 is 0, and now you can, um, so now like we have already got y and z, so we only need x this time around. So what you can do, like let's say if I can uh, take the difference between 2 and 1, that is x a2, just a second. Uh, what I was telling, like you can take difference of a. So let's forget this part right now. Um, so this this one, so that will give you a1 uh, plus 6 a2 equals to 0. So from here, I write a1 plus y we already know. So this will be from here. Like and now you can see this a1 is basically a2x. So from here, like like a2, which we I mean like we again have to enforce a2 to be 0, just like how we were like enforcing these conditions earlier, a3 equals to 0, a1 equals to 0. Now like when you do this a2 equals to 0, then you will find that uh, this will lead to uh, uh, so now you see that we have independently set all this 3 to 0. Now you can choose x equals to 1, so that like now that vector that we were looking for, like can be written in this way. So the last part, like I think I just like being sloppy there. So like if you want like able to follow that, like you can just ask me back again. So did you get? Hello, hello, are you able to get what I'm explaining here? Hello. Was this clear? Was this clear
Yes.
for everyone? Hello?
Yeah, it's clear.
Okay, then I can maybe move on. So, yeah, so this is your assignment problem. So this is assignment one, problem two. So this is related to the like uh, proving like vector spaces. Like it's just similarly, like we discussed vector spaces claim to be a vector space because they followed some certain axioms or properties. Based on that, like we used to prove them how they can construct themselves a vector space. So here also the same thing like we have to do. Like if the question was like consider the uh, ordinary vectors in three dimensions. This is right here with complex components where this ax, ay, and az are basically complex components. Um, then which of the following statement is basically true? So, um, so, so before that, like, have you people have gone through assignment one? Have you solved them? Uh, could you just let me know? Yeah, I just wanted to know, like how many of you people have gone through them? Uh, someone can say assignment one is, I think, it is the due date is already over, so I think that you have people have gone through it. So have you all gone through? Okay, like Panas is like telling like has gone through. So okay, good. So then, like I just wanted to know like if all of you is fine with this question, then I could have just gone through over on a surface level. But anyhow, like I think like maybe there can be someone who hasn't gone through it. Then I can. Let I can just do it over again. So it is the same thing again we do, like how we were used to prove vector spaces last week. So then the first statement says the subset of all vectors with az equals to 0 constitutes a vector space. So to prove that, like you can work out the same exercise. So now we have az equals to 0. That means uh, so let's say so we will take v1 be some x that is basically given. And so what was the statement? Oh, okay. So this is now the our vector is these two components. Like it has only two components, and there is no third component. So like we'll start with the first property, that is the closure property. So um, in closure property, let's say take uh, two vectors a e belongs to v1 such that is So now like we'll do closure under addition, or like we can just simply do closure under addition and multiplication both. Like let's see, like there is this C vector. This is something you can write in linear combination of A and B, alpha and beta in R. So that will uh, raised a because someone asking some question like okay, if not then yeah. So this you can write alpha x plus beta x. Someone here asking a question like I think someone raised a hand. Hello, if there's a question you can just simply unmute yourself and you can ask. Okay, so let's say I can call this something as cx cy. So now you can see this again. We found a vector. So like what we did basically, we took some linear combination of a and b, and we found something c. So which had a form cx ex cy ey cz ez, where cz is 0, and that again uh, gives you the structure of that uh, uh, vector which was defined in the question. So this one, and in the first statement, it was asked that if you keep az the third component to be 0, then this still this vector ax ex and plus ay ey with only two components, they will still construct this vector space. So um, that is what basically we proved here, uh, under closure. So this will satisfy this form. So with that, like you can also prove other properties. So let's say identity. Like, there were also other properties like associativity, commutative, and rest of like what we were doing last time. So and this one is identity. So like identity, let's say I can write some null vector is 0 ex, and by add a with 0, and that will give me a, because this is a null vector, and if I add them it, and it will give us the same structural form of vector which was initially defined in the question. So here you also prove that it has this identity element, and this identity, as you know, this comes with a inverse element. So this inverse element, like you can uh, guess it from here. Like you have to like add something with this A, such that you will uh, like generate this null vector, because null vector is your identity. So like that will be like minus A, and that can give you this null vector. So this minus A is your inverse. So like this we found inverse, identity, and closure. So that sufficiently will make it as a vector space right after setting az equals to 0. So uh, that's why like you can say this statement A is correct, and then statement B, like you, the subset of all vectors with A is equals to 1 constitute a vector space. So now like what happens if I make the third component to be az equals to 1, so then our vector would be, so like this is for the statement A, this for statement B. So az, that means v1 is ax x. Now you will see in the same way, like if you would define some A and B vectors in this v1 structure, so that will be A will be, and now like you can tell me like if mm, this can now in order to like check whether they will be closer under addition or multiplication, so you can do this same thing which we did here. So we had A and B, and then you
Yes.
can sorry, yes, I think Sujay does put the something to say. Hello, I think you were speaking like you were telling something, like you had some doubt. Okay, so can anyone tell me like if this can form a closure under this linear combination? Uh, is it okay to find one condition where it fails and then say it is not? Yeah, yeah, definitely. So like here you can see like what I was telling here in like now define a C vector that is a closure that is basically linear combination of A and B in this fashion. So that will tell you that if C is not taking that exact form, then judging that form, you can tell whether this will be a vector space or not. So like here you will see that you will get something, some ex some ey, uh, and then here you will find something 2ez something kind of that. Because you from the structure of V1, you were supposed to get only the coefficient of the third component to be one. The third component, here you can see, we set third component az equals to one. So you weren't should get this az to be two. So here in this case, this az is two. So, like earlier also, what we were doing in this C vector, you see, we found that Cz is zero because we needed that because we initially started with the statement Az should be zero, and if the Az is zero, then our vectors should have this structure. Then that's how we saw the under closure also our vectors still remain this structure where this Cz is zero. But here in this case, when we are setting az to be 1, we are finding like this vector is not attaining the same form anymore. So that's why like you see this az is 2, and from here you can conclude that it cannot form a linear vector space. And exactly like what uh, Panase was pointing out, like here since one of the condition is failing, so this is not uh, a linear vector space. So so that is for the statement B. So now I think we add some more. So the statement C says the subset of all vectors with equal components constitutes a vector. Uh, like now the next thing is like you have to set ax, ay, and az equals to both. All of them are equal to each other. So let me see. In that case, like you will have this V1 as something like it's like a um, just uh, like I've taken this as x, a, y, az to be uh, one, or like you can take anything like any uh, uh, like any number that belongs to uh, R. So that is what we started with. So sorry, like here it is told that it should be complex component. So it need not to be real. So like I've taken one here. So you take any other complex number. Let's say something alpha. So alpha will be the common factor for this entire for all the components of this vector. Now you will see that like if you do the same uh, checking for all the properties of vector space, you will find like this will form because like from intuition you can easily guess that like this can form like and this won't have some problem like we were having in this case where we were getting a very different form than the usual one because in the usual form of this statement B was like we should have a vector something of this form where the third component should be one. So that's why we had issue with that. But now in statement there is no such issue. Like you can prove the properties, and that's how like you can also prove the last statement. I think that is quite similar. So the subset of all vectors with az equals to 2ay equals to 4ax constitutes a vector space. So you can do that. Like here also you will get some common factors. You can just pull them out and and you can check this closure property, and also similarly you can go on and check other identity and other properties, like they would all satisfy well. So that was for this question. So like any questions, any doubt, like. So the correct options would be A, B, and D. So it will be A, C. Uh, Honest is asking how many properties should we verify? So it's always better to check all the properties, but the thing is like it would be very obvious like if you would just check this closure condition, identity, and uh, if you're checking identity, then it's very straightforward that you will also check inverse at the same time. And also like the thing is like you can guess it like once you check closure property and identity and one more property, like what happens like you will get a idea that it is following some structure, so that pattern will follow and it will eventually like follow all the conditions. But it's always better like to check all the properties, but for the if I mean, uh, suppose let's say if you are checking while you're checking any property and you find that 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 is not obeying the structure, or that is not, that condition is not satisfied, then straight away you can just say that like this will not form a linear vector space. So like whenever any condition fails, like let's say as we were discussing right here. So for the statement B, like right from the start, we found that closure condition failed. So we just straight away said that it cannot form this vector space. So, but yeah, I mean, for any other case, you have to check all the properties in general, but like you will get an idea. Like here also, uh, since you see like in the in statement A. So you have these vectors ax, ay. So and also you have this bx, by, which is b vector. So now you just can think like to check commutative, you have to just take a plus b equals to b plus a. So just right in your mind you can just guess like if it has to follow it, like it will be equal, so it won't change anything. Like in what case you have to be worrying about commutative? It could be if the question is about some matrices or something. So in that case uh, like uh, checking commutative is a go-to condition, so you have to check it. But like in this case it is trivial, like from like looking into, you just can easily judge. So I hope that is clear for Panas. Hello, is it clear, Panas?
Hello.
Yeah. Uh-huh.
Oh, I wanted to ask about option A. Can you go
uh,
up?
okay.
The subset of all vectors with A set is equals to 0 constitute a vector space.
uh,
Is it okay to use Week-2's notion where they say that you can actually claim that it's a subspace of 3D or three dimensions? So therefore, it's also a vector space.
Sorry, could you repeat the last part of your state?
I mean, for option A,
Right.
can we think of it as a subspace? Because
Yeah,
it
yeah,
can,
yeah.
because I see the A0, then it, or for all, It
Yeah,
doesn't
exactly.
matter. Yes.
Yeah,
Okay.
yeah, exactly. You can say it is basically the subspace.
Okay.
So so here also like we are telling the subset of all vectors. So like it is basically a subspace. You pointed out really well. So like the thing is like we have we have a global vector space which has three basis vectors. But like if you would restrict your vector space to a small region, like just taking like only uh, uh, two basis vectors of them, so you can only like uh, say that like that you have restricted your vector space to a small region that is a that forms basically subspace of that global vector space.
Okay. That makes sense.
Okay. Oh,
Thank you.
oh, fine. So if are there any more questions? So if not, like we can move on. So this is another question from your assignment. So same assignment, that is this is problem 10. So um, now the question is let V1 be the space consisting of two by two matrices uh, with complex entries and complex numbers forming the scalar field. So which of the following statements is true? So the statement one is telling both V1 and V2 are vector spaces. So in order to prove this V1 and V2 are vector space, then you have to check them in the same way. Once again, uh, so let's say like take V1. Like I think that I have missed the question. I mean, question is let me check again. Oh, sorry, actually, I forgot to wrote what is V2. So maybe I can just write what is V2. So it's similar to uh, V1, but just this is a bit different. So here, the real numbers actually forms the scalar field. So in case of V1, so there were complex numbers which were forming the scalar field. So okay, so like you can do the same exercise again. So like V1, you can write V1 is a set of 2 by 2 matrices whose entries in C. So these are 2 by 2 matrices. This is defined on the defined scalar field complex. So so to prove closure condition, again you can say there are two vectors in V1 where you take this linear combination of A and B to be some uh, any other vector that is big C, this alpha beta belong to this complex field. So you will see that like this C will also form a 2 by 2 matrix uh, whose like entries would be complex, and that will be defined on a complex field. So like, I can write something like this. So um, it satisfies closure condition, and then you can also check for identity. Identity you will find like uh, like, let's say there is some identity matrix 2 by 2 matrix, which I'm denoting by so element would be 0 because I'm doing um, addition. So we basically we are checking like this identity property under addition. So it has to be something of a null matrix or something of sort of that. So like this ij again goes from 1 to 2. So again, like you will see, if I make operation of A over the identity element, it will give me the um, same vector again. So that is how you prove identity element. So in the same way, like you can also check for the inverse. So the inverse would be something of Aij, because if you can uh, take this form, then you can prove that like if you would operate A or if you would add A with minus a, you can get the null matrix. So this is 2 by 2, this is 2 by. So null matrix is your identity element. So like whenever you operate the element with the inverse element, that will always give you identity. So this is how you check inverse. So uh, so you can say this V1 is a vector space. So in the same way, like you can check V2 is also vector space. Uh, like just the difference is like here uh, real numbers basically forms your field, and previously it was complex number. But like there won't be any change. Complex numbers are more general, like, and when you restrict to real numbers, like it will still follow those features. So V2 is also a vector. It's better if you can check the same process back again for V2. So your correct statement will be yeah, eh, that will be A. So this is clear. Yeah, uh, I think Panasa has a question.
Okay, I wanted to ask for V2, what if we say that the entries of the matrices are real and then the
Okay.
scalar field is complex? Is
Uh,
it
uh,
then that it
the
is a,
entries of V2 is real, and
if we said that the entries of V2 are real and then the scalar field is complex, what then can happen there?
what was your second part? The scale of
I
sorry,
mean, so I want to twist the question to see
yeah, yeah.
the if it is still going to be a linear vector space. So
Uh-huh.
they say let V2 be a space consisting of 2 by 2
Two by two
matrices
matrices with real entries.
and
Okay. Uh,
complex, just swap the two or complex numbers forming the scalar field. Is it okay? Is it true then to say that V2 is a vector space?
Suppose if your question is like if V2 is a space like constructed by two by two matrices whose
Yes,
entries are real,
yes,
and the field is formed by complex.
yes.
That in that case, like I think they should form because like uh, so it is just like the same vector V1.
Hmm.
So here you are just changing the entries to be real. So let's say here in this part, as I was doing like yeah, this AI this one which I was written here, these are basically elements which I said it, this is complex.
Yes.
Instead of that, like if I would have written some real, then you can check consequently they will take the same form back again. So they will be real, and there won't be much difference because like here I have proved it for complex, so you can do it for real also. So like there is nothing different would take place.
Because I have the problem with the Cij is an element of the complex. Because if you do that,
uh,
then the C is no longer an element of the complex of the reals. It's now an element of the complex. So you have
no,
removed it.
no, like Cij will again be some real thing because
Oh, okay.
here I'm supposing like going by your condition, Aij is something real and Bij is also something real. So
Oh,
it some will be also real.
yes, yes.
So So does that answer your question?
Yes, that answers my question. Thank
Oh,
you.
okay. Okay, fine. Okay, so good. Um, so like any more questions? So statement A was correct. So then we can move like, if there are no questions as of now immediately. Uh, this is your also assignment question, assignment one, problem number 6. So let me check the question also. So like in problem 6, there are some statements, and there it has asked like which statement is basically is true. So like I have written the correct statement here. So the thing is like we have to uh, prove it how. So mm, so like the statement goes like uh, just a sec. So uh, yeah, the statement is a set of mutually orthogonal vectors is always linearly independent, but a independent set of vectors need not to be mutually orthogonal. So like how can you prove this statement? Um, so let's say you have two vectors, alpha 1, alpha 2. So these are uh, Dirac's vector notation. So for linear independent, alpha 1 to alpha 2 is 0, like that implies A1 equals to A2 equals to 0. So so like at the start of this like session, we went through that question, like that question which we also partially discussed last time. So for linear independence, this is the condition that has to be fulfilled. Um, so if I can go to that question back again. So in order to fulfill the that condition, uh, not this one. Yeah, this one. So well, the condition like that we found that or we were imposing this A2, A3, and A1 individually going to 0. So that gives you some form of XYZ vectors. So this XYZ, XYZ components of that vector. So here we found that that is 100. Similarly, you can construct many other vectors. So it is not a very like unique solution that we will get here, because this system of equations here you are looking at, they are not unique. So they have many solutions. So similarly, the last time around also, like we were looking through, uh, there also we found like that system of equation were not forming a unique solution. So so that gives you an idea. Like so, linear independence need not to be orthogonal. So I mean, two linear independent vectors, they need not to be orthogonal. So like here, this uh, alpha 1 and alpha 2, like they may be like linearly independent, but need not to be orthogonal. So you can arbitrarily construct like two vectors. So which like would be like linear independent, like where you cannot express one using the other, but still but the they can be orthogonal. The like now if say that this two vectors alpha 1 and alpha 2 are orthogonal, this will imply, so this is your inner product, that is the condition for orthogonal vectors, the inner product goes to 0. So that means like if I have let's if I can generalize this more. So now if they are orthogonal, now if we want to know like they has to be linear independent now, again we can look back to the same condition that is actually, let's say if I can uh, take a linear combination of all these mutually orthogonal vectors, uh, Now, let's say if I take it inner product, take inner product, with a goes to n, I want to n, that will give it, this is actually alpha. You will find this alpha n, sorry, I mean this coefficients a n, they has to go uh, individually zero to 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 uh, to get this condition, because you will find here you can see this alpha and conjugate vectors, they like that m index that runs from 1 to n. So like when you take the inner product, you will find like at one point, like for let's say m equals to 1, you will see that uh, uh, this term will be 1, because they are mutually orthogonal. Let's say they are also normalized. So this will be 1, the inner product of this alpha 1 with m equals to 1. And all other inner products will be 0 when you fix m equals to 1. So that means you will find that this a1 is 0. So uh, like to achieve this condition, you will find when all the a's, this a1, a2 individually goes to 0. So that is basically the condition for linearly independence. So now, like uh, I was telling, this n goes 1 to 1. So this proves linear independence. So I hope this is clear. There's some issue in understanding this, but like you can just tell. So it was clear for you all. Okay, but I say again, like yeah, he's clear. I mean, he's no doubt in this part. So anyone else? There's anything to say, they can say. Also, we can move with the next thing. So if there is no other question, like we can move to the uh, other topic. So last time around, like there were uh, the questions from various like subtopics, like orthonormality. This we started with what are linear vector spaces and so on. Then we understood what basis and span of a set and all those things. So like and those things which you have also like getting yourself clarified and I mean you are understanding those concepts from your lectures that is already uploaded on your portal. Uh, so, but there were like few questions related to this Cauchy-Schwarz inequality topic. So just to for the um, so for the sake of recalling, so the definition or the inequality theorem is basically the statement goes like this. So uh, for all vectors v and w in this vector space V, so you can say that the inner product of those two vectors will be always basically it is the uh, I mean mod of this inner product of V and W will always be less than or equal to the individual. Okay, I think there is a question. Yes, you can speak.
Hello, sir. I think you forgot to square the inner product.
Uh, oh yeah, okay, yeah, right. There will be square. This is more square. Actually, this is norm square. Okay, thanks. So yeah, so this is the statement. So like otherwise, people also interpret this statement as triangle law also. Let's say like if I have a vector v, so this is my v minus w, and let me this is a, b, c where s- for the vector v and b is norm for the vector w and similarly for c. So now like if I let's say the third uh, 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 yeah this third vector, if I take the inner product square, basically the LHS of this inequality, so which I can write v minus w, that will give, so this is c square, a square plus b square will be cos theta, where theta is this angle which you can yeah this the theta is this angle, the angle between this uh, v and w. So So inner product of VW will give you AB cos theta. Because inner product of VW you can write it as norm of V multiplied with norm of W and cos theta. That is AB cos theta. So I guess you are aware of this identity. Like uh, people sometimes also like recognize with law of cosine. So this a triangle law is also like um, that is also one of geometric interpretation. People give with I mean in relation with the Cauchy-Schwarz inequality. Like like you will find this statement in various forms. Sometimes like I would say like sum of two sides of triangle is like will be uh, cannot be greater than the third side. So in that way also people express this Cauchy-Schwarz inequality. So so in this related to this Cauchy-Schwarz inequality, like there were questions in assignment. One of them is this problem 7. So uh, so I've pasted that question right here. So this is your problem 7. So suppose we consider the space of two-dimensional vectors in which both components are real. Can we define the inner product of two vectors A, B, uh, uh, such that inner product of AB is given as AX BX plus half of AY BY? So would this be a legitimate scalar product? If yes, does the Cauchy-Schwarz inequality play out here? So the first statement says it is not a legitimate scalar product. The scalar product must be defined as x bx plus ay by. So so it need not to be like a the I mean uh, the inner products that you see like usually like in when we take vectors. So like we always think of this structure, but the inner products are always calculated from the like definition of like are you people like aware of like some metric, because inner product involves the use of metric. Using metric only like you define inner products. So yeah, so when you will find the involvement of a metric in your inner product, that inner actually there is no such involvement. The metric always comes. So here, since you are working on a flat space or Euclidean geometry, so in Euclidean space, so you the metric is quite trivial. So that's why the general form always comes in this way. But the thing is like it is not really general. So uh, so the way that A dot B is defined, it can be a inner product form. So to do that, like we can check like other properties of inner product, like I think the Hermitian symmetry, linearity, and positivity. That may be, I think, like conveyed to you during the lectures. So let's say if I want to check Hermitian symmetry, then I will take B dot A, that is uh, that will be Bx Ax half of By Ay. So I just use this definition of inner product, and I did this by like flipping the places of two vectors of this uh, inner product. So you see that this form which I'm getting here. this is the same thing as A dot B. So this will, gives you a Hermitian symmetry. So for linear it, if I define CXL, C, in that case, C alpha, that means CX alpha X beta BX is alpha half of CY alpha AY plus beta B. Again, I use this same inner product definition, and then here you can see uh, you can basically write, if you can pull out the common factor of alpha and b, that will give you Cx. This I can write. So here you can see this like I can able to check this linearity condition, and it is you can say this is linearly like like operating with A and B, or I can say this inner product is linearly distributed among this sum. So I first started with C inner product with the linear combination of A and B, and then I'm getting this alpha of C dot A plus beta of C dot B. So so this is your uh, linearity condition. So and then the positivity condition. The positivity condition, like that has to be that is a condition of that inner product should be greater than 0 and equal to 0. So you take the inner product with itself, that would be a square plus half ay square, which is always greater than 0 and is equal to 0 only if this if a would have been a null vector. So this also satisfy the positivity condition. So, uh, so it basically follows all the like definition of scalar product, and hence like you can say that like, it actually forms a less dependent scalar product. So the statement was like the first statement like it cannot be true. The second statement, it says that it is a legitimate scalar product, and the Cauchy-Schwarz inequality simply reduces to x minus x by minus a by bx of whole square is greater than or equal to 0. So Cauchy-Schwarz inequality, like you can check uh, this this x bx of whole square. Now here you can see x square by square plus ay square bx square minus 2x bx ay b is greater than or equals to 0. So, so that is the condition that was given in your statement 2. So yeah, this was the uh, Cauchy-Schwarz inequality, which will finally reduce if you follow this definition of inner product. So so the statement B is correct. Uh, uh, so the the statement C and D will also not hold true here. Like the statement C is telling it is not a legitimate character, but as we saw, like it is satisfying all the conditions. So that that is a so that defined inner product is a valid one. So if there is any question, if there is like any problem in understanding this part, like you can ask.
Hello, sir.
Right.
I wanted to ask if we have a defined inner product,
Uh-huh.
does that then guarantee us that the Cauchy-Schwarz inequality is satisfied?
Sorry, if I have a defined inner product.
Is
Uh,
it guaranteed that the Cauchy-Schwarz inequality is satisfied?
uh, like as long as I think it is equivalent in span, like it is guaranteed that it will hold because we are working on Euclidean geometry. So these
Okay.
vector spaces are all like they would follow the same proper to your higher studies. You will find various other settings like you would go through Minkowskian space and all those things. Then in those places, like you can find that this Cauchy-Schwarz inequality will break.
Okay.
So as long as you are in Euclidean, like it is uh, like a very like intuitive to see that this Cauchy-Schwarz inequality will always true.
Okay. So it's only satisfied in three dimensions in Euclidean space.
Yeah, Euclidean, three-dimensional Euclidean.
Okay. Or in
It need not to be like three-dimensional. Like it could be also
n
any
dimensional.
yeah n-dimensional. Yeah, right.
Okay. Thank you, sir.
Yeah, okay, fine. So there's any more question? This no more question. Like you can go to the other part. So this is again based on Cauchy-Schwarz inequality. So the statements are given. Like you have to figure out which statement is correct or which statements are correct. So statement one says if two vectors are multiples of each other, the Cauchy-Schwarz equality for them becomes an equality. So to show that, like, let's say if I have a five two vectors z1, so which are multiples of each other. So that is Z1. So its conjugate form would be, so now if you would check for the like Cauchy-Schwarz inequality condition, then to check this. So um, here you can see mm, Z1 is taken inner product with Z2. For this Z2, I can write from here uh, 1 by alpha Z1 and this Z2 I can write is taken inner product with again with the same relay alpha Z1. Uh, Sorry, this is alpha. This will be alpha Z2. That is Z1 Z1 Z2 Z2. So this gives you a Cauchy-Schwarz inequality, and you see this Cauchy-Schwarz inequality like it can only become equality. Cauchy-Schwarz becomes an equality. Two vectors are multiples of each. So here you can see this statement 2 is right. Like others, the statement 1 and 2 are they are equivalent. Like you two vectors are multiples of each other. The Cauchy-Schwarz equality for them becomes a. So here both A and B are correct. Um, so this for certain choices of inner product, it may be impossible to find vectors. for which the Cauchy Schwarz inequality is inequality. But yeah, the statement is not correct because like also as someone was pointing out, I think it was Panase. So as long as like we are working in this Euclidean vector spaces. So we have inner products, and inner products do hold this Cauchy-Schwarz. Uh, in this vector spaces, Cauchy-Schwarz inequality stands valid. So there will be, if we are taking or if we are defining new inner products, still we would able to find some a condition to uh, uh, to see this Cauchy-Schwarz inequality becoming and just equal. So so the statement D, the next statement is consider the vector space of complex number through which the scalar product is defined as G1, G2, is G1 star G2. Yeah, the Cauchy-Schwarz equality is always an equality since any two such vectors have multiples of each. Uh, so, if we consider like a vector space of this complex numbers Z1 and Z2, and the field is also like defined of for complex numbers, that is basically a complex field. So, and if they are multiples of each other, and alpha, so that proof is also more or less is the same which I have discussed here. So here you see this z is a complex number. I'm defining as a multiple of the other complex. Sorry, these are not numbers; these are vectors. So and this alpha is in C. So that is what the the statement D is telling. So this will still hold true because the first which I showed here, Z1, Z2, they are multiples of each other. If I would not have taken this alpha to be complex, if instead it would have been real, then this proof will still go as it did. But when I'm making it complex, this will still hold true. So statement T is also a equivalent statement of the proof that we have showed you. So mm, all A, B, C, I mean D is correct except C. So all options, all statements are correct. So is it clear uh, this question? Is it clear for you?
Sir,
Yeah.
can you elaborate more on option C?
Option C.
Yes.
For certain sources of inner product, it may be impossible to find vectors for which the Cauchy-Schwarz integral. It is telling that if we have certain uh, other definitions of inner product, like the one which we we saw in the previous question. So inner product, it can be defined in many form depending on what space we are working on. So uh, so you will see that as long as we are working on this Euclidean vector spaces, you will see that this Cauchy-Schwarz inequality will hold true, and there will be still a condition So when we are saying that this Cauchy was inequality, this is Cauchy was inequality. So in this Cauchy was inequality, it has two parts. Like one is the inequality part, in which you will have only this less than signature, and there's the other part where you will have only the equality signature, only the equal sign with it. So so uh, so as I said, like when for all inner products, Cauchy inequalities, like the Cauchy inequality will hold true, like as long as we are working on equidistance space. So there will be a particular case where you will see this Cauchy inequality will be becoming an equality condition, like as long as we stick to equity in space. That was the thing which I tried to explain.
That makes sense. Thank you, sir.
Okay, okay, okay. There's any more question? There's no more. Like we can move on. So there was another topic I think that was introduced this week. That is this Gram-Schmidt orthonormalization. So what this topic or what this technique is all about, like this is an iterative algorithm, like to construct an orthonormal basis of EJ from vectors forming a basis of this form, or vectors Vj, which are not in general orthonormal to each other. So this is just a technique. Like if we are given some arbitrary basis of vectors, that is which I am denoted by Vj. So if they are not orthonormal in general, then you can uh, apply this Gram-Schmidt orthonormalization to make a orthonormal basis, this EJ. So the idea is like if I've like V1, V2, V3 are the other given vectors, then and they are not orthonormal to each other, then what we do, like we start with the vector. Let's say we are starting with a v1 vector, and it's like we try to normalize it in this way, and then like we take v2 vector, which is defined like this. So what is happening, like suppose if I like normally through intuition, as we understand, if these vectors are on a plane like this. This is B1, this is B2, and if these are not orthonormal, so what I can do first, I will uh, let's say uh, I will start with V1 vector, and I will like normalize this. So then this technique, what it does actually, we want to construct here I have v1 v2 vectors which are not orthonormal to each other. I want to make it orthonormal, so I take v1. So what I do, like v2 has two component. So like I can say this is v2 perpendicular, and I can let's this is uh, V2 perpendicular, and here I have V2 parallel. I mean the component along V1. So uh, uh, as I said, like I have V1 and V2 vectors which are not orthonormal, but I want to construct a orthonormal vectors from these two. What I can do, this V1 vector, after normalizing it, I can like uh, I can take away the component of V2 parallel, which is along this direction. So in doing so, that uh, the vector that I will left around is like this only V2 perpendicular and this new V1. So like it is like I'm removing the projection of V2 on V2 on V1. So like I had V2. So we so clearly. So I had V2 initially, and it had uh, two components, one lying along the V1 and other is perpendicular to V1. So I want to make them orthonormal. So like that is one of the conditions is making them orthogonal. So if I have to make V1 and V2 orthogonal, then I have to take a V2 perpendicular component of the V2 vector and V1, and I have to take away the V2 parallel component from this V2, so that V2 will left with only V2 perpendicular. So V2 perpendicular and V1 will together form a orthogonal vector, and then consequently we also normalize them. So that is the logic, that is the idea that so. Uh, so I think like this is also like better explained by Professor Odidasa. So that is the idea of transfer osmosis. Then that is the same thing here also in this we are doing. So first we have V1, and in V2 perpendicular we are defining which we really need that in order to construct a orthonormal basis. So for satisfying orthogonality condition, we will do what from V2 vector, from this V2 vector, we are taking away this parallel component. So when we do that, we are left with only V2 perpendicular component of V2 vector. So in the same way, if I have another vector 3, so like I would repeat the process. I have V3 vector. I will take away the component of V3, which is projecting on V1, and also I will take away the component of V3, which is projected along V2. So this E2 is related to V2. That is here. These are two, and the same way E1 is also related to uh, V1. So what we are doing, like here, as I was telling, I'm taking away the projection, this V2 parallel which I have written. So that is the equivalent term which I'm pointing right now. So this is I'm like, taking away the projection of V2 on V1. So I'm left with only V2 perpendicular. The same I am done with V3 perpendicular also. So I've taken away the projection of V3 on V1 and also on V2. So I get a V3 perpendicular component which will be perpendicular to to newly constructed V1 and newly constructed V2. That is basically V2 perpendicular uh, and V1. So that is the idea of orthonormalization. So like there is a this quick question. So like also like uh, the time, I think we started a bit late, but like maybe just not take more than like 7 or 8 minutes. So let me just quickly go through this question. So this we have given like apply the GS procedure to the following set of linearly independent vectors. These are the vectors, and uh, then we have to construct this orthonormal set E1, E2, E3 with some span, and E1 is parallel to V1. So like that is what we are starting with. Like here also we took V1 as the reference step. Like parallel to it, we were like doing all other job that were like taking away the projection along this V1 direction. So uh, okay, um, the strategy is same. Uh, we will start with V1. So let me call the new V1 will be denoted by this V1 perpendicular that I'm taking to be V1. That uh, is given 1 minus 2, 1 transform. I have to normalize this. So after normalizing, I will get E1. So that is basically like unit vector. 1 minus 2, 1. Then I got the E1. Likewise, I have to calculate E2 and E3, which will altogether form an orthonormal set. So for E2, I have to first determine what is V2 perpendicular. And as I showed there, V2 perpendicular is actually equal to, so I have one, and this inner product, uh, this inner product I can write. So, so you'll put this right here, and then after like uh, like getting the full expression of V2 perpendicular, you can just normalize it. That is again your uh, unit vector. So, so after normalization, you will get this result. So same thing you have to repeat for with the perpendicular. So take V3 and take away the projection of V3 along V1. That is same way. You have to take away the projection of V3 along V2. So now you have to So V3 is given, that is 0, 1, 2. The same way you'll do E1 plus 1 over root 6 to 1. Same way you will calculate this inner product. E2 is just the final expression which we got here, and same way you can calculate this inner product. So I think you can calculate this, and finally you will get a like, if I would write the complete normalized form, then that will be, so here you will see this E1, E2, and E3, they form a orthonormal set. So this way, this orthonormal set technique is very useful, and like is like applications there throughout. Like you will find when you like tech physics in future. So same way, like this vector linear algebra vector space is really an important topic. So whichever topic, like even uh, Cauchy-Schwarz inequality, that is direct consequence. The direct proof comes from, I mean, the direct proof of Heisenberg consistency principle, that also comes from there. So, so like you need to clarify your concepts well in solving any questions, and these concepts are very useful and very fundamental. They form a like a framework for your physics course. So okay, so that was it. Uh, and did you got this part, like this norm or orthonormal technique? I think many people have already left. So Panese was fine with it. So okay, thanks. So then we can end here, and we can meet next week around the same time with some new problems, and also some problems from week 2. So I hope you are following this lectures well, and if you have any other issues, you can like clarify right here in the sessions. And also there is a discussion forum which you can put questions there, like and and you will get an answer there. So like if there is any problem or any issues, they can like you are always free to ask. We are done here for today's session. Okay, so if not, then we'll meet next time. Okay.